today we're going to demonstrate for you how to build the very simple but very effective spoon catapult. I'm going to launch it. There we go. You didn't see it, but it flew and hit the wall very, very far. So the students are going to be building this catapult during their unit on levers and fulcrums in simple machines. And so it's really fun, and it's also an introductory lesson in physics and engineering, which is kind of exciting for elementary and middle school kids to do. In the lesson plan, we actually have you build a series of catapults, and for the other models, we give you very detailed step-by-step photos and instructions. For this model, however, we just give you a handout that has a photo on it, and the instructions say, look at the photo and figure it out. And that was done purposefully. We want the kids to struggle a little bit and kind of just figure out for themselves how to put it together. But we do want you, as the teacher, to know from the get-go how to put together. So we want to demonstrate it for you. That way, when you're walking around, you could give them a few hints here and there, but really allow them the time to figure it out for themselves first before you step in. Okay, but let's go ahead and demonstrate this. It's a very cheap activity too, which is great, and you can actually reuse all the materials because everything is put together with rubber bands rather than glue. And so you need 7 popsicle sticks, 1 plastic spoon, and a handful of rubber bands. About 10 per group would be fine. The first step you have to do is put together these 2 separate triangles. Okay, and so I'll do that for you. I'll put that together. It's just going to be an equilateral triangle, but they don't have to be exact. Okay, that's the basic shape that we want. You don't need to overdo it with rubber bands. 1 per point works fine. Okay, so I have 1 there. I'll do the other off camera and come back. Okay, so I completed my 2 triangles here. Again, each triangle is made up of 3 popsicle sticks and 3 rubber bands. Now what I have left over is 1 popsicle stick and the spoon. I am going to tape those together with a little bit of masking tape. Okay, so that's done. Now we have to assemble the catapult. And again, we look at our model. So it looks like I'm going to have to attach these 2 triangles at these 2 points, and then the spoon is going to rest right here. Okay. And again, you attach these just with another rubber band. If it seems loose, you could double up the rubber bands, but so far it's working really well. So that's 2. And then I'm going to put my spoon in between these 2 parts right here, these 2 points of the triangles. So I have to get the spoon to rest in between these 2 points right here. And you might have to do some adjustments to your design, which is the whole fun part of building your own machines. And so we want it to stay there, and the best way to get it to stay there is to use a rubber band. And so let's see, how are we going to do this? Did that keep it on? Yeah, that seems to work. Okay, so it's attached there, and then we have to figure out how we're going to attach it here. Yeah, that works. I probably should have attached the popsicle stick first and then put the spoon on, but that's fine. Is it working? Yeah, it is. Okay. So now I have my second model. I have to make some adjustments. And they're not all going to look exactly the same. So you can see with my new model and the old model, we're at different angles at this point. And the students can discuss why that is, and they can run tests in terms of which one will fling the marshmallow or the M&Ms farthest. Oh, that's not going to work. Okay, so this is the perfect point where they have to say, huh, there is something wrong with the model. We're going to have to troubleshoot that because it shouldn't be doing that. This one, if you look, is pretty stable. So now I'm going to have to figure out what it is about how I attach this to the popsicle sticks that's making it collapse on itself like that. Let me play around with it a little bit and I will come back and let you know. All right, I just spent 20 minutes trying to figure out why this catapult wouldn't work. So two things that I discovered. You definitely do want to buy cheaper plastic spoons, and I'll show you why. Okay, so here was the spoon from the original Catapult that flung it really well. And you see how that plastic is really pliable and it kind of bends back a lot? The one that I was using doesn't really bend at all, and that was causing problems. So one thing you definitely want to watch out for is the quality of your plastic spoon. So when you're buying plastic spoons for this activity, make sure, and we rarely say this, but make sure you can find the cheapest plastic spoon that you can find. You want something that's going to bend really easily, just like that. Another thing I noticed testing out the models is that for the part where the spoon and popsicle stick attached to the base of the catapult, when you're attaching this part, the spoon and the popsicle stick, to the rest of it, you don't want these rubber bands to give at all. So if you're seeing I'm bending it back and those rubber bands are not stretching, they're not really moving. Before they were, which was causing the problems. Okay, so now we're going to go into our testing trials. And what you want the students to do is test out their design, see any problems that they're noticing, and try to fix them. And I will show you one that I discovered. And again, your students are going to have different ones based on how their catapults turned out. So we know the first one that I had to troubleshoot, which was my spoon wasn't flexible enough, and so now we've replaced it with a more flexible spoon. And I noticed one more problem as I was testing out my design. And I'll show you. Let's just do the initial test. So we have to collect the data. So here's the first go around. It kind of goes straight up, then falls right down. And you're going to have students take on different roles. So there's going to be 1 or 2 students who are going to handle the launching over here. You're going to have another student who's the spotter, and they have to carefully observe where it lands before it bounces somewhere else. And so that M&M landed at 6 feet 3 inches. And then you're going to have a recorder who's going to take down the data. So we're going to try it again, just to make sure that it wasn't a fluke, and that this one flings at pretty much around 6 feet. So that one was about 6 feet 10 inches, so it flew a little bit farther than the first one did. That initial model we had in the office was flinging the M&Ms about 16, 17 feet, and I want my catapult to do that as well. And so I was playing with it and trying to figure out how I could improve the design. One of the things I tried, And again, it's going to differ with the different student groups based on whatever their catapult is like and based on the materials that you give them. So work with the materials that you have. I wanted to tighten the tension on the rubber bands here, and since I didn't have thicker rubber bands, I'm just doubling up the rubber bands. So again, I added another rubber band to attach the two parts of the catapult here so that it doesn't move at all when I'm pulling back the lever. I didn't want this to shift. So let's see if that affects the results. You'll have to have one person be the collector of M&Ms or marshmallows or whatever your projectiles are. For safety reasons, we don't want those sitting around on the floor as students are testing. So you definitely have to make sure that students are told from the very beginning to pick up whatever they're flinging, whether it's marshmallows or pieces of paper or M&Ms, right away. So again, I'm shooting for more than 6.5 feet. Oh, that was a dud. That was still 6.5. And now I'm confused because I was sure that my change in my design was going to fling it a little bit farther. So I'm going to try one more time. So that was 10.5 feet, which is better than 6.5 feet, but still not exactly what I wanted. So I have to do it one more time just to really check, because it's when you get results where it's 6.5 feet and then it's 10.5 feet for the same design, you know there's an issue there, so you retest it one more time. So that was at 11 feet. So my latest model is flinging the marshmallows about 10.5 to 11 feet, which is an improvement on the 6.5 feet from before, but still not what I want. So again, I'm shooting for that 16 feet, 17 feet. So I'm going to keep on playing with this model and try to improve my results. And that's a part of the engineering design process. It's a part of the scientific method. And so give your students as much time as the period will allow.